Hi everyone. Imagine building an aircraft wing or a bridge panel that's made from very light material that's strong enough to carry extreme loads. But if and only if every layer in that material is perfectly intact. What happens if a layer inside this material is spliced or slightly damaged? Of course, the stiffness decreases. This is exactly the challenge I'm addressing today, because we can't see that change in your naked eyes. My name is Rawan Aqel. I'm a PhD candidate, and today I'm presenting a technique called the impulse excitation technique to study the mechanical subtle degradation in composite sandwich structures. The same structures used heavily in aerospace, marines, and civil infrastructure. To do that, what I have done, I created different samples made of intact samples, core spliced samples, impacted samples, and gapped samples. And we applied a non-destructive technique called the impulse excitation technique, as mentioned, to lightly impact them and check their vibrational response. After that, we run them through the fast Fourier transform, FFT, to change these sound vibrations into frequency plots. Each and every peak in that frequency plot shown over there represent a vibrational response. The height, width, and position of that frequency plot tells us a lot. What I found in control samples, there was a nice sharp peak, meaning a strong intact sample. However, in compromised or defected samples that has core splices and gaps, what I found is that the samples, the peaks were broader, shorter, moved in position, and in some cases it was disastrous where the gap is there, where there was a huge stiffness degradation. This matters because today there is no fast, affordable way to detect that damage internally without compromising the structure or destroying the structure. My research indicates that the impulse excitation technique can do it safely, quickly, and without destroying the sample. This is a very important improvement for engineers, manufacturers, and inspectors working with advanced composite sandwich structures that are used heavily in our main industries: aerospace, marines, and civil infrastructure, I'm repeating. In the future, I aim to integrate this with machine learning to get a real-time response with a smart system that continuously detects the structural health. Because in engineering, knowing the problem early means saving time, cost, and sometimes lives. Thank you.
Hey.